Hello, everybody. Welcome to SRA 365. I'm, of course, Professor S, and this is this week's lecture. So far, what we've covered with categorical variables, if when we said we have two variables, we can explore if there's a relationship, how strong that relationship is, and if any of the observed differences between any of the differences between the observed and the expected values are significant. And that's with just two variables. But like when you start thinking about what if there's three variables that we're considering? So let's say A, B, and C. So if we do that, then we have to compare A and B, A and C, and B and C. But also another thing we have to do is see if there's a relationship between all three altogether. And so one of the things that I want to kind of talk to you about is like, how do we do that? Because chi-square test can only compare two things at once, two variables at once. So how can we compare three or more variables at the same time? And the idea is like it's kind of this way. So far, we have A, B, and C. So A, let's say, has two options on it. So there's it's a categorical variable, and there's two different possible values, like yes or no, true or false, whatever, right? And we'll say B and C are just some other variables that we're looking at. So far, doing a normal chi-square test, that's what we have at BC. But the way that we do it for A is we take all the data from we subset the data for the two options. So we say all the options, option one from A, and all the everything in the data for option two. So we subset it, and we then compare the whole data set for the relationship between B and C. So that's how we kind of get three variables all at the same time, right? So if it's true or false, so we say all of the data of the whole thing where A is true, and then find the relationships in that where between B and C, variables B and C. And then for A, where A is false, I guess was the second option that we said, all the relationships between B and C to see if there's a relationship of those different categorical values within A, right? So that's how we can get all three of them in there. If we want to keep on going and do four, so let's say the fourth variable has two options. So then what we have to do is we have to do this again and again. So the idea is that we have, remember, D has two options. So we have to do the two options for A for option one, and the two options for A for option two of D. So it just gets to be a little bit intense. Maybe it wouldn't be so much if we kind of knew what values were, but the idea is it gets to be a lot at once. And so the idea is there's got to be a way to kind of ask ourselves, do we need to do this yet? And that's where log linear analysis comes in. So the point of log linear analysis is to help us determine which variables we don't need to look at. Okay, so there's most of the time what that means is it's going to give us a model where there's going to be values that there's some sort of relationship. But the point of log linear analysis, it helps remove values that we don't need to consider because there's not going to be a relationship between them. So then what happens is it helps us remove all sorts of them. When we're just doing two variables, not that big of a deal. With three, it gets to be like saving us a little bit, but with four, it's crazy helpful. Unfortunately, we're not going to be doing four because it's pretty intense log linear analysis, but as helpful as it truly would be with four variables, I'll just be giving general examples with it so you can get hopefully that appreciation, though in practice we'll just be using three. Okay. So anyways, with log linear analysis, like the chi-square, there's two assumptions. First, that each observation must be independent. I think I talked about this before. I've said this before. Hopefully it was for this class. But the idea is that means like if we're thinking about categorical values, that one observation doesn't go into two locations. So like the example that I usually give is thinking about genre for a song, right? So say we're looking at relationships with the songs and somehow genre is one of those categorical values. So we don't have a song that fits in two different genres like country and rap. Each value that's in our contingency table should be representing one observation. Okay. And then the other thing is that the expected values are greater than 5. Okay. And there's like some wiggle room with that last one, where as long as they're like, it's not so much and whatever, but it's really, that's what, if it makes us feel the best when there's no expected value. All the expected values, are greater than 5. Okay. So anyways, the way that we do this log linear analysis is with backwards elimination. So what we do is we make the most complex model, and then we start removing variables until we come to a model that we want to compare. And so when we remove a complex model, we test its significance. So like, for example, when we're looking at these variables right here, so we have model 0, we have 1, 2, 3, and 4. So notice with model 1, we remove model 4 and we test the significance of model 1. Once we test the significance of model 1, we say, all right, so the significance is if it's greater than 0.05, then we keep on going. But if it's less than 0.05, then we say that the one before it is the model that we like, because removing that variable was significant. Okay. So the idea is that the variables that we're looking at is the comparison between different categorical variables. So like, really kind of what we're looking at here is like, if we're looking at like 3 different variables where A, B, and C are different variables, then model 1 we would think about being the comparison of A and B, A and C, and B and C. Okay, so then that means model 2, we remove one of those comparisons and see if it's significant. Okay, now removing the variables might seem like it's a brand new thing, but it's kind of not. It's like, the reason why it's new is because we're doing it by hand. So when we've done like our multiple regression before, we had the p-values, and you notice that on the right, or sorry, right up above me even, we would look at the p-values of the different variables, right? And so essentially those are calculated by removing them and finding out the significance. So that it's the same sort of thing as what we're doing. So it's finding the significance of removing it. And that's what we're doing. We're finding the significance of that model by removing one of the variables. So again, each model we test during our summaries or whatever, that's determining how significant the variables that we are removing, right? So remember, when we went from model 1 to model 2, we removed that variable 3. And if it was significant, then we liked model 1. If it's not, then we keep on going. And remember, when I say significance, we're talking about the p-value, and that it's less than 0.05. So if it's less than 0.05, it's statistically significant. Otherwise, we keep on going. Now, the thing is it doesn't really tell us that the variables have a relationship, so we need to do further tests. But the idea is, again, remember, log linear analysis to help us eliminate variables so we don't have to look at so many at once, because it's a lot, right? And so the general format for these things is we go from the more complex models down to the least ones. So notice that when we're comparing A, B, A, C, and B, C, we have variables A, B, and C, right? And then when we get down to model 5, we're just looking at A and B, and that's the only single variables that we have. The idea is, it's like we're kind of referring to this tree, is like kind of a good way to put it. So notice, like, when we have A, B, and C, we need all these things underneath it. To kind of help you understand a little bit more, I'm going to use 4 variables at once. And so in order to do A, B, and C, and D, we have to have all these different representations underneath it. And let's say that we work it down till we work to, let's say, ACD. There it is. And so if we're looking at ACD, then the different variables that we would need to compare are AC, AD, and CD, and then also the individual variables themselves, so A, C, and D. Okay, so when we're entering it into R, like when we're thinking about A, B, C, we just need to make sure we have those bottom parts of those of that tree first. Now, so I have up here the how we enter the into R. So we have the model is assigned by log lm, and notice that it's using a formula similar to how we've talked about xtabs before, where we have the tilde, and so then we have the variables after. We don't have any response because we're not finding response. We're trying to look at the relationship within the variables themselves. And so also notice that the object, the data, is not of our data frame. It's of an xtabs object. So the idea is xtabs is going to create our contingency table reference. And it can have multiple variables in it. But the idea is like it's not going to be referring to a data frame. It's referring to an xtabs object. Tables don't work. The table method doesn't work. It's got to be an xtab. And then the fit part at the very end where fit equals true, that tells R to estimate the expanded value of each cell. Okay. So anyways, when we're looking at like model 1 here and say that we wanted to look at ACD again, notice that the way we would plug it in would be A, C, and D, because those are our foundation. Then we go work up to the next level in the tree. So we have A, C, A, D, and C, D. And then we have that top part where it's A, C, and D. Okay. And notice that the data is table, whatever I called it. And I know I said like the table function object is not something that's accepted, but sometimes we call it table. I think that's what the book or the text calls it. So that's how we work it. And then what we do in our model is we remove the variables from more complex to least complex, and just so it just works its way in, or works its way in. There you go. You're mirroring what I'm looking at. And so then it kind of ends up looking at like this sort of relationship until we work it down to nothing. Okay. And so again, this is just to kind of illustrate how these things go. We don't have to worry about building these models up, so we can copy and paste it. And I'll show you how to do that in just a second. But I want you to get an idea for how the elimination is working. So hopefully that made sense. A couple of things before we get into it. In order to use the log lm method, the one that we're using for creating these models, we need the library mass. We need to load the mass package. What's weird about the mass package is that we don't have to install it. It's already there. We just have to load it. So you just say library mass and it's good. That's it. You don't have to install it. It's there. And just as a reminder, you need to use the xtab to create the contingency table. And that works very similar where you have the tilde and then all the variables that you're using. You don't have to do the relationship between them. That's what it does for you. So it's just like if you're doing 3 variables, A, B, and C, boom, that's it. So A plus B plus C. That's it. But it is what it's saying in the bottom is just make sure you store it as an object so you can reuse it in each one of your lines. Let's see. The next thing is like just to give you a heads up, I got this data set from up there. And it's a randomly generated set, so don't expect it to actually mean anything. Okay, it's just to illustrate. And I'll try to include the data set in the announcement so if you want to play with it as well. But I want to give you something else other than the dog cat one. Okay. So anyways, so you could still use the dog cat one if you want. It's just, this is like additional examples. It always seems to be helpful with statistics. So anyways, let's go into R and take a look at this. So I'm starting off with a blank canvas here. Canvas. Sorry, I'm starting off with nothing so you can kind of get an appreciation for kind of how easy this is. I mean, it looks like a lot when you're going through the text, but it's not really as intimidating as it is, or it looks. Anyways, let's kind of start with it. So what we're going to do is we're going to use the HR CSV, and I'm going to load that first. So and it's called HR And I'm going to call this HR data. There it is. And so let's kind of take a look at what this looks like. So notice that we have males and females. We have white collar. Let's see here. So we have a bunch of different options here, but the one that is kind of sticking out to me that there is it's an ordinal variable is the age. I mean there is like a ranking of it. Like the other ones there's not, but the not that one. This one. Anyways, let's see. How do we do that? So let's take a look at what it is like through here. So gotta spell table correctly. So I want to do I don't need quotes for this. HR data and age. And so notice that naturally it kind of gives it its alphabetical order. It does 30s, 40 or older, younger than 30. That's absolutely not the kind of order that we want, because it's going to when it does the comparison between these, it's going to think that this is the order that we want it, and it's not, right? The other ones, it doesn't really matter so much. Like for instance, when we look at what's the other ones, it's gender, cool, whatever, and status, blue collar, white collar, sure, whatever. But like really for me, then those ages kind of throw things off. So I want to I want to have a specific order with that. So I want to order them so that the it's let's see, so that it is younger than 31st, then 30s, and then 40 or older. And so we have to do the factor method for that. So I'm going to actually I could just copy this part right here because I'm going to use it twice. Now, do you have to do this in the lab? I don't remember off the top of my head. I don't think so, but it's not too bad, so that's why I'm showing you. Anyways, here we have the variable, and then we say levels equals, and then we have them in the order that we want them. And so first, and it's got to be like exactly the way they are in here. So I'm just going to copy them from down here. So younger than 30. And 30s. And then 40 or older. And then these have to be in quotes. There we go. All right, so then when I run these two lines, it's now a factor, and so it's natural. So when I do this table, notice that it does younger than 30, 30s, and 40 or older. Okay, so now it's like in a comparison that kind of makes sense. Okay. Awesome. So now we're ready to do our log linear analysis. Actually, first thing is like we gotta, in order to do log lim. So notice that, well, actually we'll just get the data over. Sorry, I'm all over the place. But the idea is like to kind of show you the simplicity of it. What I'm going to do is you can't see this because this is off screen, but I'm going to copy and paste the step 1 stuff that is in the text in here. Okay, and so notice it says substitute VR1 and VR3 from the names of the 3 categorical variables. Oh, we also got to do the xtabs thing, right? So what do we want to call this? So here it calls it table. So let's just save our data as that. So we'll do table is what we're calling it, and we'll do xtabs is, now remember we have to have our formula. So the formula is gender, not comma plus, status, and age. Okay, so we're just putting all 3 of them in there. That's good. And then we say where we're getting the data from. It's HR data. Wonderful. And so notice we have our xtabs object. Great. To kind of give you a perspective, when I run this line right here, it doesn't like it. Notice that it says, one, we haven't set up the variables, but that's not the reason why it's upset. It's because couldn't find function log lm. The reason being is that we have to load the library. So we have, or the package. So we have to do library and mass. So then when we run that, let it load the package up. I guess it did it. And then now when we run this line right here, now it has an error, but it's not because it can't, it doesn't know the variable, or it doesn't know the function. It's because the variables are undefined. var1 and all that, that's not things that we've talked about before. So we got to do those next. And so the idea is like what we can do in here is like we can use the IDE to help us. Okay, so I'm going to put the cursor on this line right here, and I'm going to do the search. And so then I'm going to search for var1, and I want, for each time this var1 is, I want to replace it with gender. That's the first variable I want to look. So notice it highlighted the var1, and I say replace. And then I just keep on going throughout the whole thing till I reach the end of all the models. There we go. I don't want to replace this one here, but that's fine. And then the next thing is status. So I put status here, and I want to replace all the var2s with it. I don't want to replace this one. This was just in the comment. So I want to do next. There we go. I want to replace that one. This one, this one, this one. And so notice that it is like filling out this data for us. It's working smarter, not harder. All right, cool. And it comes back to this part right here, which we don't need to change. And next thing we're going to change is the third variable, which would be, let's see, age. And we want to find the next one, find the next one. There we go. This is the first one we want to replace. So replace, replace, replace. And so we go through here, and one of the reasons why I'm kind of suggesting this instead of like searching for all of it is because you might miss it. I mean, like once you take a look at this, I mean, there's a lot of words in here, so it's easy to kind of miss the var whatever. There we go. So we've gone through all of them because it's gone back to this point here. And so now what we can do is we can X out of this search, and we're done. So we have all of our models we'll find of our different variables. And so notice the first one, it has all the different, it has the most complex one. So remember like that tree where it's all going down. So we have gender, status, age. So that's the three variables that are referenced, all the different pairs that they can go, and then all three together. And that's going to be model 0. And then for model 1, we have all of them except we take out the one where they're all three together. And then the next three, what we do is we take out just one of them, and then we take out 2 of them, and then we're just left with those 3 variables all by themselves. Okay, so what I'm going to do is I'm going to run this so I have all 3 of my models. Okay, notice that it likes all of it, and that's good. And so now the next thing that we're going to do is we're going to copy the second part where it's going to give us the guide for kind of how we think through these. Like you remember how we had the summary with the where we have to see the statistical significance when we were moving variables. So it's going to start off with model 0. So run it, and then we look at this value right here where it's the Pearson p-value. Notice that it's 1. Model 0 will always be 1. If it's not, you made a mistake somewhere. All right, so go back and check it. So it's always going to be 1. It's good to run it just to make sure you didn't make a mistake. So anyways, here for model 1, we'll take a look at this. Notice that the p-value here is 0.397. That's greater than 0.05. So we move on to model 2. And this is still greater than 0.05. So we move on to model 3, model 4. Ooh, this one's 0. right? So model 3 was definitely greater than 0.5. Model 4, this is where it was 0, right? So this is really small. And so this is the one that we like, model 4. Sorry, this was the one I ran, right? Model 4, yeah, I ran them. Sorry, it's not the one we like, this one, right? So notice that it says, if significant, stop. Model 3 is your best fit model, else model 5, right? So this is the one that we want. This one. So model 3, let's take a look at what model 3 is. So here we have model 3, and so model 3 is gender status and gender age. And that's it. That's the only ones we have to compare. So that's the ones we're going to look at. Gender status, gender age. Now, personally, I'm going to go through my way. If you like the text way of doing chi-square tests and that sort of thing, go for it. I like my way because I feel like it's easier and simpler, and I can get whatever I want from it without without getting inundated with all sorts of data that I'm not necessarily looking for. All right, so anyways, me complaining about it, I forget which ones they are. So gender, status, gender, age. All right, so let's say I'm going to call this observation X tabs. Oh, it's not this. It's gender plus status. And this is referring to the data frame HR data. And then we'll do I'm going to do chi test is the variable that I'm going to call it, but I'm going to do a chi-square test of it. And remember that when you're doing it my way, you got to turn off the correction. Yeah, so always false. And then I could just do this right here and do gender age right here. And so then just to confirm it, just gender status, gender age. It doesn't really matter the order at these, but it just matters that gender status, gender age. And so then after this, I'm going to do chi test. And so we'll start with this one to see what's significant. So notice that this seems to be pretty significant. So let's kind of take a look at what this looks like with the mosaic plot. OBS, shade equals true, and we'll call this main there we go. So notice that when we're comparing these, the only thing that's not significant, a significant difference is male blue collars. That's the observed is not too different from the expected, but everything else is either way significantly more with the white collar females, and the less for the males. And then for the females, blue collar females are way less than expected. Okay. But what about then the next thing is, it's like, all right, so we see that these are significantly different. So there's like way more white collar males or females expected, and not so many male white collars as expected. But what's how strong of a relationship is there? It's clearly a relationship. How strong is this relationship? Enter in our effect size. And so since this is a 2x2, that means we're doing a phi. We're finding phi, right? So that means we do the square root of the chi-square test, which is here. Boom. Divided by the size of the observations. So we can find the total real quick. We could just say total is sum of the observations, and it'll find it for us. And then we just divide by total right here. So we run this right here. And that's our effect size. It's pretty big. Really, really big. Okay. And then the next thing is the other relationship was gender and age. So we're going to look at what that relationship is. And so notice this isn't that strong. So we can kind of stop here, but I'm just going to do the mosaic plot just to take a look at what it looks like. Mosaic plot of observation. Notice that, remember, I ran observation just a second ago. Observation is gender and age. So I can use that same variable because this is the observation I'm referring to. And then shade is true. And the, no, it's main. What am I doing? Is gender versus age. So then when we run this, notice none of it's very significant, right? So there's that. So that's like, so then what we're able to do is we were able to identify that the relationship that we wanted to look at was gender and status. That's the ones that we cared about because that's the one that's significant. And it was, we didn't have to look at any of the other relationships because the log linear analysis was helpful in eliminating the ones that we don't need to look at. Okay. So we're done. This is what we have. Now, before I let you go, or while I still record, I mean, you can stop whenever you want, but the idea is, what if, like, how would we actually go about doing a chi-square test if we were looking at the three variables all at once? Okay, so what if we wanted to look at all the variables at once? Okay, so what if we saw that model 0 was significant? Okay, how are we to do that? So let's kind of take a look at the, so we had, remember, age and the color, like the status, so white collar, blue collar, that sort of thing, and gender. So how do we want to look at this? So oftentimes you want to kind of subset in ways that kind of make sense, like in interesting ways. So should we do like gender? Divide by gender? Why not? See how they're doing, or should we do by the status? How about status? I'm feeling status right now. So the way that, so I'm going to come up with two different subsets because remember status has two different values, right? White collar and blue collar. So I'm going to call I'm going to do blue and white. After all, this is Penn State, right? And so this is going to be the blue subset. So what this is going to do is I'm going to take all the HR data where the status is blue collar. Okay. And to kind of help me out, because just to make sure I'm naming everything correctly, I'm going to table HR once again, it helps if I spell things correctly. There we go. So I do this to find out like it's doing it for multiple things. So for blue collar, what we're doing is subset. We say the data frame that we're referring to. So this is HR data. And then we say the value that we want, right? So the variable that we're referring to is blue collar. And status. Excuse me, I'm getting ahead of myself. Status, right? That's the variable. And we want it to be, press enter accidentally, blue collar. That's the value. And then for white, it's essentially the same thing. It's exactly the same thing. Except instead of blue collar, it is white collar. Now, one thing before I do these, notice that the equal sign, there's two of them here. That's intentional. See, the thing is like oftentimes in programming, equal sign, well, when we're doing math, usually equal sign can mean a bunch of different things at once. It can be assigning values, it could be comparing values, it can be all sorts of different things, and we can go back and forth between those very easily because we understand the context. Now the thing is like in a lot of programming languages, whatever language we're using, it can't make that distinction so well. So when we're assigning values, we use the equals. So that's like for here. So notice that for try test, I have equals false, right? So I'm saying that the value of correct is going to be false, okay? But here, I'm not saying that status is blue collar. I'm saying I'm looking for all the statuses that it equals blue collar, okay? And so in order to do that relationship, I do doubles equals. Doubles equals is blue collar. If I want to do greater than, I just do greater than. If I want to do greater than or less than, I do, or sorry, greater than or less than. Greater than or equal to, it'd be the greater than equal sign, okay? And then also, in case you're wondering, not equals is done by exclamation point equals. If you didn't know that, that's a very common not equals sign. So anyways, I'm going to create these two subsets, and what it does is create two data frames. Notice that the blue collar, there's 475, and the white collar, there's 126, right? And so notice for our data here, we have 475 for blue, and where's white? Oh, it's going to be down here. White, 126. 475, 126. So what it did was, here, we're going to take a look at white. Notice that it's like we have the same three variables, except we've removed all the ones where the status isn't white collar, right? Likewise with blue collar, it's the exact same thing, but we remove all the observations where status is not blue collar. So male white collar 30s, that was in the original one, and that's what remains. Okay, so now we're going to do the relationship between, let's see, the other two relationships is age and gender, right? So we'll do OBS again. We'll do X tabs. And that is, well, it's still going to be age and gender, right? Is that the one that we liked? Oh, it's age and status was the one that we liked. Oh, well, anyways, we're doing age and gender here. So we do age and gender, and then this time the data that we're referring to is blue. Okay, and then everything else we'll do is the same. And then I'm going to do this again. So copy and paste it. And so I'm going to change, do the same. So instead of blue, I'm referring to white. Okay, so the white collar. So looking at the blue collar, there it is. Notice that it's not significant. So let's do mosaic plot. Shade is true, and the title is well, we can do like this is like specifically the blue color. There it is. Notice a bunch of white, nothing very significant, right? And then I'm just going to copy this and change it down here because this is going to be exactly the same thing, except instead of blue color, it's going to be white color. And I got to make sure I run this whole thing because otherwise it's going to be using the different observation. There's nothing significant. It's all the observation is pretty much close to the observed. So what if we wanted to compare the ages. Like, I mean, like the thing is like before, let's see, it was gender and age, right? That's which was one that we liked a lot. It was the gender and status. So what if we want to do the subset of the ages? Okay. So what I'll do is so here I'll just give me a second. I'm gonna you don't need to watch me type all this. I'm gonna type all this stuff up and then I'll talk to you about it in just a second. All right, so I entered in the data, and remember, since there's 3 different values for our for the age, right? So it's younger than 30, 30s, and 40. We got to create 3 different subsets, right? One for each possible value. Now, one thing that I want to move on, that I want to show you before I do it, is like, look where I have 30s as a possible name. When I run it, it doesn't like it. The thing is that you can't start with a number. So even though I want it to be in the 30s, it should be, I just did 30. So anyways, I have each one of these here. And so I'm going to actually run each one of these and we'll just go through the table. So let's take a look at those values. So here we have the younger than 30. And notice we're comparing the status versus the gender. And notice this is significant. Let's see, more than expected. And then let's see, the next one was 30s, significantly more than expected. And then 40, also significantly more than expected. So there is some significance, but then the question is like, how does age affect any of these? So when we look at the chi-square test for these, so I'll do gotta do the chi-square test for the whole thing. So for the younger, there's a significance here. There's significance here. And there's significance here. Oh wait, no, look at this. It may incorrect. Didn't like something here. Was that true for this one? Yeah. Yeah, so notice I get these warning message for each one of these. Look at what happens in here. So expected. I'm going to do this for each one of them. All right. So ages. So here's the younger than 30. If you look at the expected value here, notice that there is less than 5. Remember, that was one of our things that we wanted to make sure that the expected value was greater than 5, and here it's not. So we don't like it. But also notice that here we have expected value is less than 5 here as well for females, white collar. And here it's less than 5 here. So notice that the expected value for each one of these for females and white collar positions is really low, and it didn't like that. The thing is like we can argue that, like I said, it was allowed us to, this doesn't really help argue what we're trying to do. So even though each one of these chi-squares is significant, since it violates the assumption, we kind of question it a little bit. And notice, like before, like essentially what we were doing, we're comparing 3 variables, right? And before, when we compared the variables, when we were talking about the status, notice that like for here, when we were doing blue collar, age versus gender, it wasn't significant, right? Or age versus gender for the white collar, also not significant. So the idea is like adding the age isn't significant, right? Because remember, when we found the relationships, when we were looking at the specific relationships, it was, let's see, gender status was the only one that mattered. But that was the one that had the relationship, right? And it was a strong relationship, very strong relationship. But it had nothing to do with age. So again, the idea was we were able to dismiss the age altogether from the log linear analysis. Now, can you always eliminate one of them? Not always. Sometimes having all three of them is helpful. Sometimes it depends upon how you look at them. It kind of is misleading this way, where we compare, like we were able to do the age and do the comparison of two variables that we knew were statistically significant, right? The relationship was strong with them, but it was misleading because it didn't really, like the age didn't really affect any of them, right? It was just the same relationship each time. It's just age was consistent throughout the thing, which would make sense because age doesn't weigh into it. Now, again, all this data is made up, but hopefully this helps illustrate some of the relationships with the log linear analysis. Hopefully this helps. And again, this data should be available in the announcement. And I'll see you all later. Bye. Hey everyone, I hope you enjoyed that video. If you did, please press the like button below. It lets me know I'm doing something right. If you have any questions about any of the content, please send a message in Canvas to both me and the rest of the teaching team, and we'll get back to you as soon as possible. If you have any suggestions for how I can make these videos better, please leave in the comments below. Don't forget to roundhouse kick the subscribe button and ring the bell to get notified for when I post the next video. Anyways, I think that's good for this video. I'll see you all later. Bye.